Perfect. Okay, I got a whole slide to myself. My name is Matt. I'm a data scientist for a company called imbalanced. They're based in LA. And what essentially we try to do is infer someone's problem-solving ability from like a video game-like simulation. So I take all of the telemetry data and then I munge it into something that we can actually use, and then I build models to predict various aspects of cognition based off of that. More importantly, though, I actually got my start in data science through this group. So if this is the first time you have had any experience with data science at all, and I'm just telling a bunch of words that you have no conception of, don't worry, I was in your exact same spot. We had a smaller room back then, though. All right. Oh, yeah, and I'm UBC grad. Please hire all of this lovely cohort. Okay, so we'll be talking about the Talking Data Science competition. And this is just, they actually had done a competition previously that was actually relatively similar. But just some background on what Talking Data is. They are China's largest independent big data service platform. So my understanding of this, and I may be wrong, is they kind of act as like a third-party app store. The important part for us, though, is they get 3 billion clicks per day, which is big data, which is a hassle. So they have a problem, and it's this. It's people who sit on a chair all day and then click on apps with hundreds of phones. So what will happen is, say, like an ad company will pay someone to click on their ad and then buy the app, or not buy the app, but just click on the app. And this is a really big deal in China. It's just coming up right now. And Talking Data is looking for ways of detecting this. By the way, oh yes, question, please.
Can you explain a little bit more how this scam works? They buy an ad with their company's own money, and then it's like they're just...
Yeah, so it's going to make the app go higher in the App Store. And I think also ad companies also will buy clicks as a way of showing that their ad network is more effective than the other ad networks. And it's just kind of a race to the bottom where everyone is buying clicks. Yeah. Yeah, it's great. And like honestly, until someone posted this picture, I had no idea what we were actually looking at. They didn't give a ton of information as to what this competition was, but this really explained it for me. Okay, anyone else? All right, let's talk about the data. So this is actually a very simple data set conceptually. You have 5 categorical columns, which are IP, app, device, OS, and channel, which is just like the ad publisher. And those are encoded as numbers. So 5 categoricals plus a date time column. So that's not interesting at all. The only thing that is really interesting about this competition is there's about 250 million rows, which makes things a big pain in the butt. And then what we're trying to predict is something called is attributed, which essentially just means what happened over there. If the company has previously attributed that click to be fraudulent, that's what we have for the data set. So here's what it actually looks like. Again, you have a ton of IPs, a few more apps, a couple of devices, OSs, etc. So the first thing that really struck me about this data set is that there is really not a lot to work with here, right? There's no numerical columns, for instance. So you can't do any kind of means or medians or anything like that. And because everyone has the exact same amount of data, I was really curious what everyone was going to do in order to, win this competition. Hey, what's up?
You can maybe repeat it. Did they throw out the useful information in IPs?
Yeah, so they're all anonymized.
Repeat the question.
Okay. Alexi asked, did they throw out the useful information for IPs? Yeah, so you can't do any geolocation or anything like that. Really, what you can do is you can see if, did the same IP address have a bunch of fraudulent clicks? Probably these other ones are going to be fraudulent as well. But yeah, no fancy tricks in terms of being able to bring in new data sets or whatever. Okay, here's what the data set actually looks like, and this is like on the order of hundreds of thousands. We were given 3 days of data And then the test set is kind of the fourth day, but only select hours. And that was important because a lot of people, when they were doing validation strategies, if they thought that date time was truly important, they would validate on the third day for the hours that were being tested for, if that makes sense. Okay, so unique values, just getting an idea, doing some EDA on this data set. So click time, obviously every value is basically going to be unique. I think there might have been, actually there was a very small data leak in this data set that someone found, I think a week before the end of this. A data leak is some amount of information that, in this case, the Kaggler gets to know about that isn't helpful for talking data at all because they can't use it in the future. But is helpful if you need to get this last little bits of score optimized. So what happened was if you group everything in a very specific way and you find two rows that are duplicated, one is going to be a 0 and then the last row is going to be a 1. So that is not helpful at all for any real world application, but it did raise people's points by 0.004. It was 0.0004. So people were talking about it and were very mad about it. Okay, so the other interesting thing about this data set is it's extremely unbalanced. So if we're looking at, we should just be paying attention to this plot right at the bottom. So 99.75% are zeros, and then you have 0.25% that are trues or ones. If you've worked with an imbalanced data set before, you know how frustrating this can be because a lot of the classic algorithms that you're going to use, unless if you do something to change the way that they act, will just go, oh, everything is a 0. I got 99.75% accuracy. And it is very hard to convince a model otherwise. So there are a lot of little interesting strategies that we'll talk about later. All right, so the way that this competition was scored, by the way, I don't know how much money was at stake here. I did submit an answer to this. So of, I think, 3,600 people, I got 3,500. So, yeah. Thank you. Yeah. So that was just taking a super small subset of the data and just running XGBoost as a baseline. And then I started running it on the full data set, and it took me many, many hours. And eventually I was just like, I don't want to do this anymore. So instead I just waited to see what everyone else was doing. And it worked out all right. Okay, so in terms of scoring, what's up?
What did you want to say?
Sorry.
I missed which algorithm you said you ran.
What's it on?
I missed which algorithm you said you used.
Yeah, so I used an algorithm called XGBoost, which is just like the classic Kaggle algorithm, and there's a lot of good reasons to use it. It's not sensitive to changes in distance, so you don't have to do a lot of scaling. It does imputation automatically, and it's like relatively fast. So it's just like a good first approximation whenever you're doing something. In this competition, I'm not going to be talking a ton about the models. There's a few interesting ones from the top guys. But in essence, everyone used basically the same thing except for one guy. And the only thing that separated like the people who won big versus the people who didn't was like how they validated stuff and like what kind of feature engineering did they do. So this is ROC. This is an ROC curve, which looks really weird if you haven't seen one of these things before. So essentially what you're looking at here is if you imagine like a classifier and you're giving probabilities out, right? In like a well-calibrated classifier, you would want to split on 0.5. So everything above 0.5 would be a 1. Everything below 0.5 would be a 0. But sometimes you want to make some trade-offs. Maybe false positives are more important than false negatives in this case. And essentially what the ROC curve does is if you start at the bottom left right there, it's essentially saying like everything is going to be a 0, right? So I'm saying everything like at 0.01 is going to be, oh, let's see. I always get this confused. Does anyone else want to answer what an ROC curve is? Okay, so, okay, did I have it right? Did I have it opposite?
You might have it opposite, but it doesn't.
Okay, the important part is if you go all the way to the left, it's like very, very extreme, and essentially you're saying like nothing can be in the positive class. And if you get all the way to the other extreme here, everything is in the positive class. So what you want is you want a perfect square where you have perfect specificity and also perfect sensitivity, which essentially just means like you have a perfect classifier and that your model is really, really sure about stuff and it is always right. So this is just one of the things that one of the nice things about ROC is it's relatively good about this imbalanced data set. All right, any questions about that? I should say that like the top score was pretty great. It's 0.98, blah, blah, blah. But basically everyone was getting at least 0.9. In fact, there was someone who released their kernel and it was like 97, and everyone just took his results and submitted it, and it was good enough to get silver in the competition, and people were also angry about that. It turns out like sometimes Kagglers get angry about competitions. All right.
Do you know how the ROC curve reacts to a really high class imbalanced? Is it kind of robust against that?
So there are ways to make it robust against that. And I'm trying to remember. Oh, because what you can do is you can actually change like what is a positive and what is a negative, and then you can average out. You can do like a micro or a macro average of the different classes. So you can do that in order to get like a generalizable multi-class ROC, but you can also do that in order to help with this imbalanced data set. Does that make sense?
Yeah, I just thought of one thing. So what really matters with the ROC is just the order of the predictions, right? So it doesn't really matter what numbers you're predicting. It just matters that all of your ones are predicted higher than all of the zeros.
Yes.
And all the ones can be predicted 0.01 and all the zeros can be predicted 0.001 and you still have a perfect classifier. So
yeah.
Sorry, one more thing on that is we have had some presenters here go over this in detail. Bruce, the other Bruce, often does it. So those videos are up on YouTube if anybody is really interested in this ROC, because it is a bit of a confusing scoring mechanism.
Anyone else? All right, cool.
I think you were asking about the prize money?
Oh, prize money. I don't know. It was like $100,000 or something.
No, 25.
Or 25K?
25K, half for the first team, and then
Yeah, that seems about right. So it was about 25K, and then half for the first team, and then probably some smaller amount for the second team. I think it was only like top three were in the money at all. Yep. Okay. Yeah, and all three of them were nice enough to do a write-up, so we'll be covering all the stuff that they did. Okay, so this was mostly an excuse for me to explore big data. So my personal definition of big data now is if it's a pain in the ass to do, then it's big data. So it's just dependent on your computer and the libraries that you use. And we have Wes McKinney, who is a good sport about this. He's the creator of Pandas, saying the rule of thumb is have 5 to 10 times as much RAM as the size of your data set. So in this case, I believe if you had all of the rows together, it was something like 16 gigs as a CSV. And then if you wanted to do any kind of feature engineering at all, which is what basically the only thing you can do in this competition, it's going to balloon in size. Oh.
You mean that the text file was 16? Well,
Yes.
but the text file is all text, it's all
Yes.
string. It's going to be way bigger than it when you read it in memory.
Yeah, no, it becomes, so like the thing about pandas, and this quote actually comes from a really great article by Wes McKinney about the future of pandas. By the way, pandas is the kind of the data science library in Python. But he's talking about the future of pandas and how it's going to involve a lot of these like out of core operations, which I'll talk about briefly in a little bit. What happens is the typing system in NumPy, which is also the typing system in Pandas, will treat strings as like these very generic objects and give them a lot of attributes that they don't need. So they become extremely inefficient. So as soon as you start adding in strings, it gets really bad. But even like if you have just raw numbers, what will happen is unless if you cap it at, say, because it does all this type inference right at the start, it looks at the first maybe 1,000 rows or something like that and says, oh, this is a number, this is a string, this is, well, it doesn't actually do date times, so you have to do that separately, but etc. Right? But it'll always choose the biggest option. So that would be like a floating point 64-bit number. So what basically everyone does, and I didn't do in my tiny little example, is they turned everything into some kind of unsigned int, because there's no negative numbers here. And that is one way that they kind of like crush this down into a data set that they could manage on their laptop. But even then, as soon as you start doing anything, especially because Pandas tends to, when it creates new columns, will also create columns of a very expensive data type, it's going to explode, basically. So, yes, if it's a pain in the ass to do, then it is big data. So what does that actually mean? Well, the biggest instance in Amazon right now is like 2 terabytes of RAM. So big data isn't real anymore. You can just write that home. So while I was actually doing this competition, I had a bunch of free credits on Google, and I just thought, well, what is something really stupid that I could do with it? And I rented a 256 gig instance and started doing something called automatic feature engineering, which is essentially a way of doing fancy SQL statements in a Pandas data frame. Go for it.
Is it feature tools?
Yes, it is feature tools.
Okay, I like it.
I like it too. There are some issues with it, which we can talk about. We'll rap about it. So I was doing that, and I woke up the next day to see all the wonderful features that had been generated, and it crashed. It actually had a memory error and just dumped everything. So having a huge amount of RAM doesn't always solve your problems. You do have to be smart with it. You can't just go, oh, I'll just keep on buying bigger ones. Like this 2 terabyte one probably would have handled it, but I don't really have money for that. All right. So I want to talk about a really cool library instead. This is called Dask, and this is like, I just love this GIF. It doesn't really explain a ton about what Dask is, but I love it. So Dask is this wrapper, or you might want to call it like an engine for out-of-core computation in Python. And this has been a really big issue because as our data sets get bigger, it's getting harder and harder to fit everything in RAM, especially when you have that 5 to 10 times cost. And Dask's way of handling this is to just imagine a gigantic data frame and cut it into a bunch of little pieces, right? And then you distribute those little pieces either like onto your hard drive or to different computers. So one of the cool things about Dask is it's a very clean interface, which I'll show. But in order to go between like multi-threading, multi-processing, and cluster computing is literally changing like a single option. So it's really nifty. What we're seeing right here is the start right at the bottom is the actual cutting apart, and then a whole bunch of very basic operations. So you could kind of imagine what tends to happen with these kind of operations is you do some sort of group by, say group by IP address, and then you'll do some sort of summary statistic, but because there are tens of thousands of little grouped IPs, you can do those independently and they won't affect each other. So you can just distribute that up throughout everywhere. So there's a little bit of like startup cost for this. So I wouldn't recommend this if you already have something that you can fit in RAM, but I found it actually like really nifty. So this is literally all you have to do. You replace pandas, like import pandas as PD with import Dask data frame as DD, do read CSV. You do the group by exactly how you would. In Pandas, the API is almost exactly the same. The only difference is you do this compute step when you actually want to finish everything off. So what it's doing, and essentially what it's doing is very similar to, say, TensorFlow, where it's creating like this huge like distributed graph, right? And then the compute part actually goes through and says, okay, now I'm going to execute, right? There are other kind of out-of-core libraries in Python that I explored. The big one that people are talking about right now is called Ray, which formerly was called X-Ray. And I believe it was from the guys who built Spark originally, Rise Labs. And so there was a software engineering friend of mine who was like, oh, why would you ever use Dask? It's slow. Like you should just be using Ray. So I used Ray, but it doesn't have support for group by operations yet. So, which is kind of like the whole reason why you would do this. So don't use Ray yet, but I'm sure Ray is going to be great in the future. All right, any questions about Dask? Oh, I should also say that Dask, for this specific application, it looks just like Pandas, but you can actually generalize it to literally any function. There are certain functions, obviously, that are going to be more expensive than others to calculate. So if you want to do an exact count versus an approximate count, that exact count is going to be a lot slower. There's a bunch of different rules about like what works fast and what doesn't. But it's actually really well documented for a library that I haven't really heard about much until I started doing this. All right. So if you're willing to spend a little bit of money, but not a lot of money, I would really recommend BigQuery. So this is a Google product, and essentially it just acts as a gigantic SQL table. So in this case, I saw a lot of people just take the 250 million rows, put it into this BigQuery, and then all of their feature engineering that they did was just doing like group by operations actually in BigQuery and then downloading the results of that and then merging things back into their like actual data set. It's super cheap. I've played around with it before. It didn't cost me basically no money. And for whatever, well, not for whatever reason, because they want you to use it, the first terabyte that you download, or the first terabyte that you query, every month is free. So if you're doing something small like this, then it's going to be like pretty easy. And this is a pretty sweet Pandas API for this, and this is just the exact same thing as what I was doing with the Dask data frame. So this is, I'm sure there are a lot of people who are just starting out, and the question that I always get asked is, oh, what language do I need to learn? SQL is actually a pretty good option. So like Pandas with Python is great. R is also great, I'm saying through gritted teeth. But SQL, like, you can get a lot done if you have something in a database, and you just don't have to worry about all the overhead of, Pandas or any of the R data frame stuff. Yeah, this took me maybe 5 minutes to set up to do for this kind of thing, and the execution was extremely fast. So the thing with Dask, because I was using like a small kind of data frame that was only like 1 million rows, that was somewhere, let's say like 30 seconds. This was almost instantaneous. I think it was just like the latency for download. Any questions about that?
I just wondered.
I just wonder, did you run all this code in your own laptop or on the cloud?
Well, this I had to run on the cloud because BigQuery is a cloud service. When I was actually doing this competition before I decided I didn't like it, I ended up buying more RAM on my desktop, and then realized that that's no substitute for actually, paying attention to data types and stuff like that. I think a lot of people, they kind of talk about their setups, the winning teams. I think the top winner had something like 200 gigs of RAM or something like that, or there were 3 people who had between them about 200 gigs of RAM. But I think there were also people who did quite well on only 16. And it's just like how you use the data. and finding like a really good way of having a fast feedback loop will do a lot better. I'm showing you all of this stuff right now, be like, oh, look at all these great technologies, but really I want to talk about undersampling, which is like the ultimate big data technology.
I was just going to jump in though to say that like that cell that he just had on the screen runs happily on his local computer. It's just the query itself is running somewhere else, but all of this code you can run locally. Yeah.
You could download my notebook. You would have to change this like from statement to like some project that you set up on BigQuery, but it took me like 5 minutes. And it would just run just the same. So yeah. Undersampling. So it took me a very long time to figure out like when would anyone ever use undersampling, because kind of one of the dogmas that you hear is like you always want more data. But in cases where you have an extreme like class imbalance and also a ton of data, undersampling works really well. And basically, I want to say all of the people that I looked at, or I guess all of the people except for one who had like a crazy setup, did undersampling in a very like smart way. So there's a bunch of different ways of doing undersampling. Kind of the classic way is to just randomly select from the majority class and remove a data point each time. So this is really fast. It's unbiased, but you will lose a little bit of information. So there are other ways of doing this that usually involve some kind of like k nearest neighbors kind of selection that you can see in imbalanced learn. Generally what they're trying to do when they're doing this kind of undersampling is they want to keep the most informative data points. Like the things that are going to be on the decision boundary, they want to keep all of those because those are going to tell you more about your data set than the things that are way off base, right? For this particular data set, because there's no really concept of distance, everything is categorical, it doesn't really matter too much. But you could imagine, say, I don't know, looking for gold or something like that, and you have a whole bunch of like different data points. You probably want the stuff that is, you know, either the gold deposit or the things around the gold deposit to tell you like where else should I look for gold. You don't want things that are way off base, and especially if all of those things are also negative. Does that make sense?
Yes.
Okay, great. There's also get a mic first.
So with such an imbalance, how much undersampling do you need to make a difference?
So it varies. This is kind of like a choice that you have to make. The winning team, though, went from that 99.75 to 0.25 to 50-50, which is like crazy to me. So they threw out about 99.5% of the data and just said, this is good enough. But they did do some smart stuff to kind of balance that out. I also saw people who were doing like 3-to-1 or something like that. But yeah, they were throwing out a ton of data.
Did some teams do multiple undersampled data sets?
Yeah. I was going to get into it a little bit. You've completely ruined this presentation for me. Yeah, so, it's actually like a really smart idea. It involves, they call it like bagging, where essentially you do multiple undersamples, right? So maybe you now have 5 different data sets, but you kind of pool the information together. So you'll train a model on each of those 5 data sets and then average the results from this undersampled data set. And that hopefully will help with, well, maybe one lost an important point of data near a boundary, but the other 3 have that piece of data, so they will continue to go on. But yeah, that's generally like a really good practice, especially when you are undersampling like so greatly. So like the other thing, like the really important part about this is like your time as a data scientist matters, and your computer time also matters, right? So like what all of the winning teams essentially did was either they had like a crazy setup, or they found a really good shortcuts to get something that was a close approximation to what the leaderboard was, and then they just like iterated like a ton and did a bunch of experiments. Where meanwhile, like a lot of other people, it seems like looking at was really nice. There was actually a bunch of people who, in the top 1,000 or so, also gave like their advice of like what would they do different. Iterating over the whole data set where, if you're training one model, a relatively simple one could take 1 or 2 days, like is not going to work in this kind of environment where there are other people who are doing, maybe 5 or 10 models a day. Anything else? Good. All right. Cool. This is what undersampling looks like. I'm not really sure why I needed to show this. I just thought it'd be nice because it does have an API that is very close to the scikit-learn API. One of the weird things I found in this competition, and I haven't really seen this in a lot of other places, is this was a very like R-heavy competition for basically no discernible reason. I think what happened was the first person to get out their like EDA first submission script wrote it in R, and then everyone just kind of like blossomed from that original script. But there was absolutely no reason for them to do that because I didn't see any R-specific like packages that would be useful. And I didn't really see a lot of people using this undersampler. I think they were just like picking randomly. Yeah, this is exactly what would happen here. I had to do a little bit of funky stuff with the click time column because the undersampler doesn't like date times. But yeah, that's that we go from having, say, 100,000 rows. Yeah, 100,000 rows down to 500. All right. Okay, this is where I very sternly talk about data leakage. So Kaggle is really good for like learning a lot of really great applied techniques, but in terms of actual practical use, sometimes that takes a back seat to getting the absolute best score possible. And data leakage in general is something that I see a lot of that if you work in industry, you can't get away with, whereas in Kaggle you totally can. So I saw a lot of people essentially take the test set and the training set, and there was also like a supplementary set, so all 250 million, and calculate summary statistics on the whole thing. So they were calculating stuff like IP address, like how many times did a certain app appear on a certain IP address, right? By including the test set, you have now biased your training sample in some way, in a way that you can't really see by yourself until you start submitting things and you've realized that you've made models that are overconfident. So what can happen with like an AUC kind of metric is you're really, really confident. You're saying, oh, I got like 99%. And then you actually test it against something that you don't know, and it's way lower. And it gets a lot worse when you're actually doing this like in production, because you're also going to see things like a model drift or data drift, where things slowly change over time. So if you start fitting to your test set, you are going to have a really bad time. The big case that I saw here, and I totally understand why they did it, was using BigQuery to get summary statistics for absolutely everything, and then joining that into their undersampled like data sets. That's not good. You shouldn't be doing that. But they did anyway, and I think this guy actually won the competition. But don't let the fact that that guy got like $10,000 or whatever stop you on your path of actually doing good data science. So yeah, because there was only one kind of test set, this kind of works for Kaggle, but it does not work in real life. Okay, so what's kind of interesting, I don't know, I personally think this is interesting about the data set, but I would understand why people think it's incredibly uninteresting, is the big difference between the top models in this competition was actually the validation strategy versus any kind of model. So I'll just get this out of the way. The model that basically everyone used is something called light GBM, which is like the extreme gradient boosting, only it was built by Microsoft and is, I think, especially good at sparsity. But my understanding now is XGBoost and light GBM are basically at parity in terms of features. But for whatever reason, light GBM was just like the thing that everyone used. So there wasn't really anything interesting that I could glean and give you guys. But what I did see a lot of was different ways of doing validation. And one of the reasons why was there was that date time step. So the canonical way of dealing with date times is to have like a cutoff point from which you do not predict anything. So when you're doing validation, you would say train on the first 2 days and then predict on the third day, right? But people also really like cross-validation, so they just kind of ignored the date time step itself and replaced it with summary statistics of the date time. So like, say the hour, or like how many clicks, how many fraudulent clicks happened in the previous hour, which I also think would be a little bit of a data leak, but stuff like that, and then just doing cross-validation. There's no correct answer here. It's just a way of you thinking about this problem. But it is something that you do have to think about. And again, everyone who, won talked about their validation strategy was very important for them because they were able to iterate really fast on their stuff. Any questions about that? All right, cool. So we can actually talk about like what people did. Okay, first prize. They just threw out 99.8% of the data and it worked great. They also did this bagging, which I already mentioned. In the feature engineering, which I thought was going to be really important. So I haven't really mentioned this before, but feature engineering just means taking a whole bunch of, you have your one set of data, and you want to add things that will help your machine learning model figure out what is right and what is wrong. So one example of this is, let's say I got 40% on a test. So what does that tell you about me? Well, it probably doesn't say something great, but if I say that the average amongst the class was 20%, that actually looks pretty good for me. So that extra little bit of information is really helpful, especially for these tree-based models, so the XGBoost and stuff like that. They're very good at finding these kind of little pairwise interactions. So all they did was just very basic stuff. So just group by SQL, and that was enough because they just ran thousands and thousands of models using this big classifier system, and also a single neural net. And it seemed like they included it just because someone worked really hard on it, and it kind of worked. But yeah, they did the time series split. But yeah, that's it. Like, it was just kind of like a nose to the ground kind of thing.
I was just going to say that this kind of shows how similar the zeros were, because if they undersampled 99.8 and they did this 5 times, that's only 1% of the data.
Totally. There was some other EDA stuff that I probably should have showed, but essentially there were like some problem IPs where it was obvious that they were kind of click farming, and then there were a ton of like legitimate customers. So like there were just whole people who were like, if it's this, then it's a 0, right? If it's this, we need to take a bigger look or a deeper look.
In all of their undersampled data sets, did they use all of the positive samples, or did they also? Yeah. Okay.
They used all of the positive samples. Everyone used, as far as I can tell, everyone used all of the positive samples. And sometimes they even did something called SMOTE, which is oversampling. I think that's a really bad idea of using SMOTE because everything is categorical, and SMOTE is another kind of distance-based thing. So it doesn't really have a kind of a conception of what. So the IP, I should be talking about this, right? The IP of 1 and the IP of 2, like there's no information, there's no ordering there, right? So to say like, oh, what would the IP of 1.5 mean is totally meaningless. But I did see a lot of people use techniques that assumed that there was meaning in there. And maybe it had some kind of noisy effect to it and helped or something like that, but I'm guessing it actually hurt them. These guys didn't do any of that as far as I could tell, but I did see a lot of people doing that. I think it was just like, oh, here's a cool thing for us to try. Oh yes, actually there was a really cool thing that they did do. I'll talk about this a little bit. So categorical feature embeddings. You see this kind of more with neural networks, because the idea of a neural network is you want to learn the features. You want to learn things that will help you, predict in the future when you get to the very end of the neural network. But what these guys did was something slightly different. Instead of making feature embeddings based off of neural networks, they used a whole bunch of different topic models. So they used non-negative matrix factorization, latent Dirichlet allocation, and latent semantic analysis. So those last two are kind of NLP type. Oh, you want to talk about non-negative? Because that's fine. Sorry. Okay. I'll answer what a topic model is and then answer this. So a topic model is an unsupervised technique where what you're trying to do is figure out what are the different kind of clusters. So I'll just talk about it in the case of NLP because that's where it makes sense. So you have a whole bunch of documents and you want to start categorizing, for example, is this a philosophy paper? Is this a science paper? Blah, blah, blah. And then you also want to find out what words are associated with philosophy or science, right? So especially latent Dirichlet allocation, what it will do is it uses this really complicated, scary Bayesian function to find like the optimal way of putting words in documents and topics in like the proper probability. So essentially what you do is it's unsupervised, but you look at, say, like the top 5 words of a given topic, and if it's like Kant and Heidegger and et cetera, then oh, that's the philosophy topic, right? But it is completely unsupervised, and a lot of times you'll get really weird topics like punctuation or misspellings. HTML tags is a favorite, but yeah, that's what they do.
Yeah. Going back to that IP and categorical feature, the way they presented IP addresses were kind of interesting. Was it like IPv6? So what was that, like the numbers that they used?
Sorry, can you speak up a little bit? Yeah, it's literally the numbers.
So it wasn't like real IPs. They replaced it with a number.
Yes.
Do you know, like, was it just by the time then the IP came, or was it like related to the actual IP address that it had?
We don't know. I think they were smart enough to randomize that. But I am not
That's
sure.
actually not smart. That's actually removing like valuable data, because you were talking about considering IP as a like category. I would actually argue that it can be like continuous, especially like if you're looking at the specific IP ranges. And if you know that this is a forum and they had like, hundreds of devices coming, in theory, it should be from one IP because they're probably using like network address translators, but they could be like in continuous range. So basically what I'm saying is that the people who were using it as a numerical continuous feature, they had a point there.
Except for like my supposition and what everyone else was looking at was that essentially the number that you're giving as the IP was just a hash and has no, like, there's no way of telling if you have, say, the lady who was pressing all the buttons, the two phones, if let's say they were on VPNs even, right? Like it could have been like entirely different. So if we actually had the true IPs, then yeah, there were definitely like sub-range stuff that we could do, right? Or what would probably be even better is to find like their geolocation and go, hey, everything in like Shenzhen is fraudulent, or like a lot of things are fraudulent. But we don't have that, so we just have to say that they're categorical.
Okay, so that could be useful, right? It's just
the
way they presented the data, it's just became on kind of.
Yeah, I think it's probably like a data privacy thing. Like it's probably
sure, makes sense.
Yeah, you don't want to say, hey, here's literally everyone who's used our project, and we think some of them are fraudsters. Any other questions?
Thank you. Some Kaggle user embedding methods, I think. In this situation, he used two categories. So I think it is it called the effect kind of cross term. What do you think?
I'm sorry, could you restate the question?
I think this method is a kind of cross term, interaction term. No?
Yes, dimensionality reduction. Is that what you're talking about?
Yeah.
Yes, so it's essentially compressing the, in this case, what they would do is they would take, say, one IP, and they would look at all the apps that were used by the IP and say that that is a sentence. And they were trying to distill the essence of all those apps that were used. So that's where these kind of topic models come in. So each one of them, I believe, had, yes, 5 topics, right, and 3 types of embeddings, right. So they were trying to squeeze maybe what was a very long sequence into only 5 points, and then they would then use that as more features for their training. Essentially, they just kind of like did a bunch of stuff and just tried to see what would work. I don't really buy that this was super helpful, but the difference is between 09821 and 09828, which in kind of the upper level of Kaggle is quite a bit. So there probably is something to this. I think what's essentially going on is it's trying to find nonlinear relationships between all these different combinations of categorical variables.
Thank you.
Yeah. Anything else?
Thank you. So here, what I guess is that they use 3 methods for the topic modeling and use 3 of them as a features.
Yeah.
In that. Okay, so I think a lot of people are talking about the topic modeling thing is that how we can validate if it works properly in the model.
Well, in this case, we know that it works in that it made their number go up, right? In like the classic problem of topic modeling is you don't know when it works, right? And you don't know when you get to your optimum because it has like convergence issues. In this case, I think non-negative matrix factorization, which Ducky was talking about, it doesn't have that problem. Is it a linear process? Okay, I have a good feeling about non-negative matrix factorization, that it doesn't have the same problems that LDA, latent Dirichlet allocation, do. But besides that, really all they were doing was they were seeing, hey, when we add this set of features, does it make the thing, like make the score go up or down? And that's all they cared about. Like, I don't think they did any kind of interpretation as to what these things meant. It was just like another thing that they could put into their data set. And they made 300 more features and got 0.007 AUC for their trouble. And here's just, this is mostly just, so if you come back and look at my talk and want to see what they were doing, I just think it's so weird that they're doing this. But yeah, you can see that they actually do turn it into a literal string and then cut it up into tokens, the count tokenizer, and then do LDA, which just seems like an inefficient way of doing it. But they won the competition and I got 300 or 3,500. So what do I know? All right, second prize. Yeah, they subsampled for training. The final model was trained on all of the data. This is another case of just like a 9 to 5er kind of competition where they made, it says here hundreds, but I think this was one of the ones where like they had made thousands of features, but none of them were interesting. Like when they talk about it, it's like, okay, I guess. But they just ensembled a ton of stuff. This is like the classic Kaggle solution, where you make a ton of features, not a lot of them work, and then you train a ton of different models on them, and you kind of average all of the results together, and lo and behold, you get something that's pretty good. All right. Third prize is pretty interesting because it was the only one to use like an honest to goodness neural network for the actual classification. But it is very weird, and if you are like a neural network expert, you can kind of marvel at this thing and wonder how it was made. So I have the code right here. So there's a bunch of really weird things going on here. So if you are not a neural network person, don't worry about this. Essentially what it is trying to do is take all these different categorical features, turn them into a dense embedding, which is what the first place team was trying to do, only they're using a neural network to do this. And then they do a bunch of stuff that, honestly, it doesn't make a ton of sense to me. They do something called Gaussian dropout, which is a version of just kind of removing your data as you're training. But you don't see Gaussian dropout very often. There's this GRU, which is like a recurrent type neural network, which, okay, makes kind of some sense. But then it does batch normalization and dropout at the same time, which my understanding is that's kind of a no-no. And then it uses a prelude as an activation function. I'm sorry for everyone who is new to this stuff. I can't really talk about all of it, but suffice it to say, I think what happened here was someone was doing a ton of hyperparameter tuning to this neural network because it does not look like a normal neural network, at least in my experience. Anyone have any comments about this?
I just want to ask, what exactly is Gaussian dropout?
Yeah, so it was in the original dropout paper, and to be honest, I started reading it and then trailed off, just hoping that no one would ask that question. Yeah, but I think what happens is instead of doing in regular dropout, it's by weight essentially, right? Where it's just like a Bernoulli yes/no, and Gaussian takes into account the whole kind of field of the layer.
It would actually be slightly, well, not more. The efficiency would suck less on a lower feature space like this. So it's actually viable in that regard.
But why not
in a wider feature space? Well, because you could get more information that way.
Okay.
In a wider feature space, you would sit there and watch it go for hours or days.
Huh. Interesting.
It's normally not a good idea because normally we have lots of features.
Right. Interesting. Okay. Good answer. Yeah. Please extrapolate if you can.
No.
Okay. Fair enough. Yeah, please. Yeah, so this is just really weird, and the guy said that he tried many models, and this was kind of the only one that really worked for him, but got third place, so that's cool. For prize, again, a lot of just thousands of features. One of the interesting things that I saw was this weight of evidence encoding, which I thought was kind of nifty, but they said it didn't really work. So weight of evidence is essentially you take, for any category, again, you're doing another group by, and you look at the number of events. So in this case, a 1 versus the number of non-events, or sorry, number of non-events versus number of events, although it won't really matter. And there's a way to smooth this, so you don't have to worry about divide by 0 if you're going to question that. But essentially what that's kind of supposed to do is actually give the machine learning model some direct information about the nature of that class versus just giving it a number and having it figure it out itself. So the example that you would use here is, say you have one IP address that it's like a real problem child, and 99% of the things are false or are fraudulent. You kind of want to tell your model, whatever model it is, that right away, and it will just zoom in on that one piece of data and say, oh, this is what I really need to be looking at, and then kind of move stuff around like that. At least that's the theory of it. Again, they said that it didn't really work so well, but it was an interesting idea, and I want to try it out, so I thought I would share it with everyone. Yeah. All right. So next slide is basically the last slide, and it's just it's something that I hadn't seen before, and I thought was really cool. So if you have a bunch of questions, now is the time to ask. But so apparently the classic way of doing this kind of problem, so this kind of click detection problem, is something called a factorization machine, which is if you are looking at, say you're Netflix, right? And you have a ton of movies and a ton of users, so you have a really sparse matrix. And you need to figure out, what is what is Matt going to like to watch? because he likes all of these things, but he doesn't like these things. So essentially what you can do is you can factor that matrix, and you can get a whole bunch of people who act a lot like I do, and then from them, look at things that they really liked, and you can recommend that movie to me. So a factorization machine is very similar, only what it will do is it can actually act in many dimensions. So it's kind of like a generalization of matrix factorization. And the guy who got 6th place actually wrote, you can call it a library, so he wrote code in Keras, which is a neural network library, to do this kind of operation, and I had not seen that before. So the reason why you would want a neural network is you can also start putting in embeddings on your matrix. So for example, maybe going back to movies, I like action movies, crime movies, or whatever. That can kind of exist in the latent space of movies. So it will say, oh, The Godfather. It'll kind of learn that I would like things like The Godfather. And so you can use neural networks to actually learn those kinds of embeddings. But yeah, this guy wrote a whole package about it and then wrote about it, and I thought it was really cool. So it's definitely worth checking out. Okay, questions? Oh yeah, okay, yeah, sure. Ooh, sorry. No. Are you on? Oh, there we go.
So NMF is quite computationally intensive. How does it compare with like neural nets in terms of?
You said NMF?
Yeah.
So NMF would probably be like, so NMF also involves like a stochastic gradient descent, if I'm correct, right?
Okay.
A neural network will be probably, well, it depends on the hardware you have, but if you were to just do a CPU to CPU, like the neural network is going to be way more expensive. Because essentially, not only are you trying to do like the gradient descent on the single matrix, even if it's sparse or whatever, you have like many matrices you're trying to do gradient descent on, and then you have to do the back propagation as well. So yeah, I would guess that NMF is actually going to be faster than neural networks in pretty much every case.
Actually, I had another question. The undersampling plus bagging, could you explain that a little bit? So bagging is boosted aggregation, right?
Yeah, so in this case, we're looking at like a bagging ensemble, right? The way that people normally hear about bagging is through like random forest, where you're doing a random subsample of both the data and the features. In this case, you could kind of imagine it as they're only taking subsets of the data points, right? So they're bagging in only one direction. And there's a bunch of like statistical research that I do not understand that says that this is actually a really good idea and we should keep on doing it. So I'm just going to trust them and say that, yeah, it probably works. It seems like probably the way to do this, where, if you only have a single model, for instance, a single data set versus the 5 data sets, you have that opportunity of finding something, you have the opportunity of overfitting a lot easier on that one data set, because you can find like a really weird, one weird trick to find everything inside of your validation set, but not inside of the wider test set.